Hello everyone, I'm Zack Settel from the SAT and from Music 6D, and we're going to present our paper today on navigable music listening experiences. Here is what we will present today. Before diving in, we begin with some basics. In everyday life, we navigate our surroundings, moving here and there while turning our heads as we focus our attention on different parts of the world around us. We are experts at navigating our sonic perspective in 6 degrees of freedom. Sonic perspective is at the core of our work. In both real and virtual listening applications, a microphone is placed somewhere in the world, and we hear a particular blend of sounds according to each sound's distance from that microphone. By changing the position of the sounds, we change the mix, which we can also change by moving the position of the microphone. We're talking about the same zoom-in effect that we experience when roaming about conversations and cocktail parties. A navigated listening perspective can reveal otherwise hidden features of a musical structure, overcoming sometimes intentional timbral masking effects in some instances. The ability to zoom in on musical structures raises a magnificent, if not passionate, question about the intended listening experience from a compositional point of view. Basically, in pre-recorded music and in live music, an intended listening experience implies the use of a singular, fixed, pre-established listening perspective, a sweet spot of sorts. It's worth noting that in our approach, such a sweet spot would correspond to one particular location within the 3D music scene, which, like any other location, could be navigated to or from by the listener. To address these problematics, we created an end-to-end pipeline. At the core of our pipeline, we have a 6 DOF mastering section with a plurality of unique listening perspectives. Our pipeline's first section. In capturing the instruments and the room, the quantity, quality, and positions of our microphones are chosen to uniformly capture acoustic energy throughout the space. Zone capture refers to audio that's captured by a microphone at a particular location in the acoustic space. Mic placement, especially among the instruments, is key. When mics are too close to the instruments, the capture lacks liveliness, since the acoustic energy of the neighboring sources is missing. Inversely, when the mics are too far, near-field audio is not captured, thus the range of sonic zoom is limited. For instrumental capture, our use of conventional recording methods and techniques provides us with a well-understood point of departure. It also ensures that the audio that we capture is of the highest quality. Room microphone density, choice, and placement was informed by discussions with author and recording engineer Jean-Yves Munch and with the Montreal Symphony Orchestra's veteran tonemeister Carl Talbot, who knows their symphonic hall intimately well. A conventional stereo master targets a single listening perspective from one point in the captured space, whereas a 6D master targets a plurality of different listening perspectives at different points in the captured space. A conventional stereo master is a rendered piece of audio content. It is final, whereas a 6D master is a renderable 3D virtual audio scene. It represents potential. The arrangement of microphones for the capture session corresponds one-to-one to the arrangement of the sound-emitting objects in the virtual scene. Shown here is the instrumental mapping. The same here holds true for the way we map the room. We want to be able to navigate a listening position anywhere within a single virtual audio scene such that the rendered audio at one position is distinctive and well differentiated from the audio at other positions. Zooming in on particular instrument zones yields a high degree of differentiation and detail. The stereo image fidelity of the orchestra changes appropriately with distance. The balance of room and instrumental sound sources is preserved. Wet to dry ratio controls the balance between room sources and instrumental sources. Near-field dynamics controls the quality and amount of sonic zoom that is applied when listening very close to instrument sources. Source localization degree controls how clearly a sound source appears to emanate from a specific location in space. For each source, we can describe curves to define these parameter values as a function of distance. We can also define source node parameter values directly, which is especially useful when fine-tuning the mix. Authoring techniques borrowed from conventional mixing approaches allow for instant adjustment of isolated, partial, or total mix element groups. The scene's parameters are adjusted interactively across a number of different listening positions, iteratively refining the mix. Rendering is done in two stages. Changes to the geometric state are computed and then translated into corresponding DSP parameter changes. Our system renders output streams in standard and custom formats such as binaural, high-order ambisonics, Satosphere, 31-channel, VBAP, etc. The output can be split into separate near-field and far-field streams, as we do in the dual rendering example. Here you can see how sections of our pipeline integrate Unity and SuperCollider. Some noteworthy features: a high-density, real-time dynamic DSP graph, limited only by computing power, hybrid integration of point source and wave field representations, highly optimized multi-core DSP using Supernova, network-based architecture for distributability and scalability, and platform independence. And now to conclude, what we have learned. Microphone capture strategy plays a decisive role in the outcome. Denser room capture noticeably improves overall quality, while making it easier to balance the mix in the 6DOF mastering process, clearly worth the trouble. Near-field processing significantly extends listening perspective zoomability and potential hearability of musical detail. In the future, we would like to make it easier to control stereo imaging of the instrument and room source groups. We'd like to experiment with an array of second-order ambisonics microphones for room capture. We'd like to experiment with spherical microarrays to capture a given instrument, which then will be rendered as a multi-directional sound source in our virtual scene. And we'd like to experiment with multi-directional audio display systems such as the audio dice to render the near field. Finally, for anybody who wants to access the code and/or the data for this project, we've provided the following links. Thank you.